Good afternoon, everybody. My name is Miron Voin. I'm from Technion, and my subject is Cherenkov wake amplification by confined medium. I'm supposed to start with some introduction in Wakefield acceleration techniques, meaning the acceleration in the plasma. But thanks to a wonderful talk of Dr. Malka, I don't think I have to spend the time on this explanation. I will only point out one obvious fact that while accelerating particles in plasma, the energy for acceleration is delivered by the driver. Would it be the intense laser pulse or particle beam? The plasma itself acts like a kind of sophisticated transformer, facilitating energy transfer from the driver to the witness beam. The case we are considering is a different possibility, is to store the energy for acceleration in the medium itself. Extract this energy by stimulated emission of radiation to a Cherenkov wake, and then use this wake to accelerate the trailing bunch. So the Cherenkov wake in the bounded active medium. We are considering a circular waveguide filled with an active medium similar to that of a laser. A trigger bunch or a train of bunches propagates through this waveguide. It triggers weak Cherenkov wake, which, as we will see, may be amplified by stimulated emission of radiation from the active medium, and then a certain distance behind the trigger bunch, another bunch or train of bunches of electrons may be injected in phase with the wake, and this trailing bunch will be accelerated. In our model, we represent the dielectric function of the medium by a simplified formula consisting of a frequency-independent coefficient and a single resonance at frequency omega 0 with bandwidth of delta omega and multiplied by omega plasma square. The omega plasma may be found from standard laser theory as a function of a growth rate coefficient alpha. Let's assume for a moment that omega plasma is 0. In this case, we are dealing only with passive dielectric. For the charge propagating through our waveguide, the magnetic vector potential may be represented as a function of the radius of the R and the parameter tau, which is actually a time delay between the position of the triggering bunch and the position at which we measure the field. This vector potential will be a sum of infinite number of eigenmodes of the same waveguide. GS here is a radial green function, and under the integral in the denominator we have a second-order polynomial. The solution of integral is trivial, and it depends on the sign of Cherenkov condition epsilon bar, meaning that if the velocity of the charge is below the velocity of electromagnetic wave in the same medium, the epsilon bar is negative, and actually this is the epsilon bar, and the wake will consist of the sum of evanescent waves. And in the case epsilon bar is positive, meaning that we exceed Cherenkov condition, the wake will consist of propagating waves. Each wave will have its own eigenfrequency, depending on the geometry and the PS corresponding 0 of the Bessel function, and the phase velocity of all the waves is the same and equal to the velocity of a trigger beam. If now we replace the epsilon r by our function for dielectric function of a medium, and we find the electrical field in z direction, we see that it is proportional to this integral having the fourth order polynomial in the denominator. One of the solutions of this integral is unstable and corresponds to growing wake. And in the case that one of the agent frequencies of one of the modes is approximately equal to the resonant frequency of the medium, this the unstable root of this polynomial will have this form. We will return to this delta omega d in a moment. The condition for the resonance is simple. We just have to select appropriate radius for the waveguide for the chosen mode. So let's consider the spatial growth depending on our delta omega d. Just for reference, for example, for laser pulse propagating in unbounded active medium, the spatial growth will be described as exponent of alpha z. But for Cherenkov wake in the waveguide, the exponential growth, the spatial growth will depend on the delta omega d. And for two limiting cases of epsilon bar, it would depend on alpha divided by epsilon bar, or in our case, square root of alpha divided by epsilon bar. But the epsilon bar is a very small number comparing to unity. So we actually our spatial growth for the Cherenkov wake is expanded by several orders of magnitude comparing to the growth for the laser beam in unconfined medium. This fact may be illustrated by simple geometrical interpretation. Consider a laser pulse propagating in active medium distance L. Its gain will be alpha L. If the same laser beam will propagate at angle theta through the same medium and will reflect from some walls of the structure, the effective gain will be alpha L divided by cosinus theta. Cherenkov wake propagates at theta Cherenkov, such that cosinus theta Cherenkov is equal 1 divided by beta by square root of epsilon r. And the gain for Cherenkov wake will be alpha by L by square root epsilon r, which is approximately 1, divided by square root of epsilon bar, which is very small. Let us see some simulation results for this model. I will not go through all the numbers. I will just say that we used as a characteristic of our medium for simulation characteristic of proven laser systems based on CO2 at high pressure. We consider the mixture of CO2 at pressure of 10 atmosphere. Lambda 0 is 10.6 microns. The waveguide radius is about 50 millimeters, and the resonance mode is chosen to be 360. What is important that the trigger beam is modulated by 20% in density at the frequency, resonant frequency of medium omega 0. So this is the spectrum for the wake at a distance of 6,000 lambdas behind triggering bunch. In total, 2,000 modes are considered, and you can see clearly that the resonant mode 360 is about 5 orders of magnitude above any mode consistent which built the wake. On the insert, you can see the comparison between the case when the resonance is exactly at mode 360, which is a blue line, and the case when the resonance just in between of mode 360 and 361. And as you can see in the last latter case, there is a significant degradation in amplification of the wake, several orders of magnitude, and the wake is not completely monochromatic. At least two modes contribute to the wake. On this graph, we see the dynamics of the spectrum of the wake as a function of distance from the trigger. The green line corresponds to the amplification of resonance mode only, 360. You see that it is fairly exponential, but if we consider the sum of first 1,000 of modes, which is the red line, we can see that after approximately 3,000 lambdas, there is no difference between two lines, meaning that after 3,000 lambdas, the wake is dominated by the resonant mode and is actually a monochromatic wave. Here we consider two cases of resonance is exactly in 360, which is blue line, and resonance in between of 360 and 361. We see that the dominance of modes close to resonance became evident only after about 5,000 lambdas, and there are still signs of intermodulation. So exact geometry corresponding to resonance on the single mode is critical to have conditions for acceleration. And oops, no. Here we observe the effect of modulation of the trigger beam. Red line represents the trigger beam modulated by 20% in density at the frequency of the resonant frequency of medium, and the blue line is for the beam of the same charge but not modulated at all. You see that amplification degrades by 2 orders of magnitude. And to conclude, we presented an analytic model for the amplification of Cherenkov wake in a cylindrical waveguide filled with CO2 mixture and 10 atmospheres. We had shown that if one of the eigenfrequencies of the wake is approximately equal to resonant frequency of the medium, this mode of the wake will be amplified by stimulated emission of radiation. The growth rate will be enhanced by reciprocal by inverse of Cherenkov slippage factor, which is on the scale of 1,000, and a trailing beam of electrons located many lambdas behind the trigger bunch in phase with the wake may be accelerated. Consideration of nonlinear effects of the saturation are presented in the poster session by my colleague Zeev Torker. Thank you very much.
Thank you very much. Questions to the speaker? I have a question. Can you show the conclusion? Do you mean the electrons have to go through the 10 atmosphere CO2 laser?
It means that it's a mixture of CO2 laser at 10 atmosphere. So what is the question?
The electrons have to go through this medium?
Yes, have to go through.
What about collisions and so on?
Of course, we have to consider in the forward investigation what will be the effect of the ionization, which will take place, what would be effect of elastic and inelastic collision. Some losses of energy are of course expected. That's true.
This may be dominant.
We still do not. This model doesn't take into account the elastic and inelastic collision. Let's say we have to introduce another parts of the spectrum of the CO2, including that parts which will where we will have decay and not the gain of the energy. That's right.
Okay, thank you.